everyone. I'm Sam Green. I am the founder of Cambrian. We are focused on providing financial data and financial intelligence for agentic execution. Quick background about myself. I worked for 5 years in national security doing cryptography, top channel analysis, and then got a PhD at Santa Barbara, focused on reinforcement learning and efficient neural networks, how to design efficient neural networks. Also co-designed or I designed the first optimizer for Odos, which is a DEX aggregator, rest in peace. So recently I came across a cool article from a group called DDS Research. Has anybody heard of them? Okay. And they were talking about basically there was an academic study showing that you could have used GPT-3 to build a long short strategy and then profitable for several years. So when people say, oh, can we get alpha from LLMs? Well, it's definitely been done. And if you do it naively now, it's all squeezed out. So you can't repeat what has been done in the past. And I think that one of the reasons that you can't naively use GPT to get alpha, to get an edge, is because of the latency that it takes. So specifically, the strategies that were looked at in this research were long short strategies. So they just looked at headlines. They looked at if the sentiment was positive, neutral, or negative. If the sentiment was positive on the asset, they would go long on it. If it were neutral, they wouldn't make a change. If it was negative, they would short it. And they saw that they were able to take GPT-3, so old leg GPT, and they were able to take it, and GPT-3's cutoff was before the news that they backtested on. So they took GPT-3 and then they started sentiment trading with it on news after the cutoff date for GPT-3. And they showed they were able to get a Sharpe ratio of 3. They had some assumptions about fees. Of course, that's always a problem with backtesting is your fees. It's harder to take into account like prop impact and fees. But still, it was interesting. But so researchers have duplicated these studies. There's a bunch of great papers on this topic, and they showed that if you were to take a model and then start backtesting it on data, I think this was GPT-4, which had I don't know when its cutoff was, but they took GPT-4 and then they started backtesting it, and they showed that in Q1 2024. If you were to do long short trading on sentiment, then your model would be right 62% of the time. But then by Q4 2045, all that alpha had been squeezed out. So the strategy stopped working over time. With the implication that this technique was already being used in production by traders, large traders. So for you or for anybody, unless you were optimized and highly optimized, you would be able to capture this. This got me thinking. A lot of my PhD was about how to design efficient models and how to distill. I wrote one of the first papers about distilling RL models into high performance RL qualities into smaller models back in 2019, I think it was. And what this visualization shows you is this is without this selection. You have 3 models, and the opposite, what I saw back then, this is like obvious now, maybe it was obvious back then. But if basically if you took an RL policy, this is all vision-based RL on a target video games, classic environment. And what I saw is that the bigger the model you had, the faster the thing would learn, and the better it would do in general. So red is the large policy network. And you can see that it almost always not always, but almost always learns faster, it gets a higher score than the medium size model. These are all CNNs, convolutional neural networks, and then the small model. So this is what you did by default. If you just take a large, medium, small model, trained from scratch, large models learn faster, they reach a higher plateau than smaller models. And so the technique that there was already some papers on distillation out, a couple papers from Google at that time. I think they started writing those papers in 2018. The first paper I think is in 2018. So basically, you can take your environment, you can take a large policy, you can have it interact, learn from the environment, so get it to become high performance. After it's learned from the environment and it's plateaued in performance, you can then have it interact with the environment and then record the states and the actions or the basically the logics that come out of the teacher network, record that to a big database, and then you can take that big database of observations. So you can be basically treated like a supervised training problem, and then use all that information to start exploring with smaller networks. And it works really well. I mean, distillation is magical. That's why you're seeing it in the headlines. It basically always works. And here you see that the bold numbers on the left scores, and you can see this was the teacher scores of the teacher network. These are the scores of the students. They never actually got to experience the environment. They just learn from the teacher, and then they interact with the environment. No fine tuning after distillation, just like the raw distillation result. And you can see the scores are about the same or better. So this is how do you apply this technique with LLMs? Well, you get tons of news. You start building a corpus of news for the assets that you're interested in trading. You then use an open model, or you use, the Fable. You can have it start doing sentiment analysis on all this stuff, and then you can start taking you can create embedding vectors for the output of Fable, and you take the news as input, and you create a supervised training corpus, and then you can then start experimenting with smaller models. And you want smaller models because you want hardware optimized models for latency. And then quickly, one other technique that I worked on back then was how do you do architecture search with hardware constraints in mind. Latency is a hardware constraint. And so this is like a toy example showing you have the right input with then two elements, you have two weights, and then you have these weights that determine how much you have the softmax weights that determine how much these are taken into account. And what you can basically do is you can assign a cost to each of your hardware operations. And so in a transformer, this could be to how many layers you have. And you can actually then take that cost and combine it in your loss function. And you can start optimizing for hardware costs. For example, for latency. And you can start doing basically a hardware search or an architecture search that takes into account things other than just error, but also latency in this case. And here you can see that basically you have this knob. This is your controllable knob that will basically allow you to control the how many resources are used. So this knob you can see here, when you turn down the penalty on hardware costs, you will tend to get larger neural networks. And when you start multi-fidelity on rubber, you get smaller networks, and then what these dash lines are is the performance cutoff, the acceptability for minimal performance. So you can find the sweet spot on performance. So this could be, yeah, so you could, or for using LLMs for trading, you could track like how long it took to get it work it out. So I think, yeah, that's all I have. Pretty good at some questions. Have James.
Okay, Jonathan, although you missed a lot of the talk.
Question at the end. What methods do you use for the useful to that type of approach, like some optionality, or did you have to develop some pickers?
Well, how did I do it?
Yeah.
PyTorch back then, just hack on PyTorch for months.
But like, is there like an optimization method behind it? Like,
PPO.
or you're using the BPO to do that? Or
So the RO one was all PPO.
okay.
This one was just gravy. So.
Okay. And
Background why student unsupervised data, C hallucinant analysis, explore other methodology.
Yeah, so that's when the LLMs started, or the transformers were really starting to take off back then. And I was wrapping up my degree, and so I was just hyper focused on getting some final papers out. And so now I did.
Has anyone studied like how manipulatable this like semantic analysis based trading is? Like if everyone knew you were start doing this, start replacing things with DAPs and things like that.
I haven't seen that, but they're kind of a related topic. Is best paper awards at NeurIPS last year was somebody that had a pipeline in the title, and they showed that if you give the same question or same prompt to many different models, and then calculate like the distance between the embedding vectors of outputs, they're basically identical outputs. And so I duplicated this on basically I took a bunch of statistics about like order data, the same snapshot, and I gave it to a bunch of different models, and then calculated the distance between the embedding vectors of the outputs of those models. And the text is almost identical between many of them, especially like the Chinese ones and the, like Anthropic. And they're just almost identical results. And so I do think that this is a good avenue to collaborate for study. Is like, even if you learn how to manipulate one of them, it might translate to others.
Okay, that's super interesting. Actually, I'm just going to connect this to another combo I heard about yesterday from Brendan and Jonathan. Jonathan, that's you. Oh, let's see. Yeah, and Quintus actually. Something we were trying to do with the block loader on Ethereum that we run is let people upload trading strategies that are private, but obviously you can, see that people will start uploading sandwiching strategies, trades to like screw people over. And so I think someone had the idea, or it was a mix of people, to maybe try to translate those strategies to an embedding and see if they're similar to a known malicious example. I think Brandon has some cool ideas on that there.
Yeah, so just for context, there's some existing work that we've done on turning models into vectors and doing inference on the results in the vector space. And the approach is actually very similar to what you're doing in the sense of like, we take a bunch of queries, we run them through the model, and we can make sure it's out of their outputs. That's an N by D object. We know how to get distances of N by D objects. Now we have statistics to make sure. So if we analyze that, And we have found that a lot of like model covariates correlate with distances in space. And so you will find things like if you find a jailbreak for one model, there will be like a radius of like an effective radius for the jailbreak and stuff like this.
Yeah, that's really cool. Have you started to publish this?
Yeah. It's, it's in the transcript. The relevant citations here, I would say, are comparative foundation models using data kernels, and tribal perspectives of the graph and language models.